Always takes a moment. Great, okay, and then this one. Okay, all right, we're sorted, we're ready to roll now. So I would like to thank everyone today for joining us for our Schedule A of this Monsoon Seminar Series. And so today we are joined by Dr. Paul Betka. And Paul is a structural geologist who uses field data sets to study tectonic processes. He was first drawn to geology as an undergraduate student, where he became intrigued by the morphology of the valley and ridge provenance of the Appalachians in the US, and of course the processes which shaped those in general. He has a degree from the University of Vermont and a PhD in geology from the University of Texas at Austin. Since then, Paul has been a mapping geologist for the Alaska Division of Geological and Geophysical Surveys, and then he was a postdoc and a research scientist at Lamont Doherty. And then now Paul is an assistant professor at George Mason University, where as we were just discussing before the recording here, that he loves introducing students to tectonic processes and structural geology of mountain belts. And so, without further ado, I would like to hand it over to Paul for the rest of his talk. And I would ask that you hold back any of your questions until the end of the talk, but feel free to type them into the chat and then we'll read them out and discuss them at the end. And so, take it away, Paul.
All right, thanks a lot, Tara. I really appreciate the invitation to present, and I also appreciate you accommodating a unconventional time because I was teaching earlier today and wasn't able to make the regular time. So anyway, the talk today is late Cenozoic tectonic and climate interactions recorded within the ancestral Brahmaputra Delta. And the picture you're seeing here is a landscape view of the state of Mizoram in Northeast India. And this is right the heart and soul of the Indo-Burman ranges. It's a very beautiful place to work. And the ridges there are, of course, mostly fault cord anticlines that uplift and expose the Oligocene, Miocene, and Pliocene section of the Indo-Burman foreland basin. And so, as was mentioned in the introduction, I'm actually a structural geologist, and the focus of most of my research deals with mapping and modeling the tectonic evolution of plate boundaries, and in this case, particularly the Indo-Burman ranges, which is located here at the northern end of the Sunda subduction zone, just where it joins the collisional part of the Himalayan origin. And it's a fascinating place to work for structural and tectonic and seismic hazard reasons, because it's the planet's largest example of subduction accretion. The massive Ganges-Brahmaputra Delta has something on the order of 16 kilometers of sediment that's burying the trench at the Arakan megathrust and being accreted in the Indo-Burman ranges. So much of my research focuses on really the structural evolution of the fold belt and the present day seismic hazards associated with convergence across that margin. However, that is not what I'm going to talk about today at all. In fact, today I will present two recent papers from our group, as well as some recent PhD work from our colleagues in Mizoram that discuss really the late Cenozoic depositional history of the Indo-Burman ranges, and then in particular, the detrital zircon uranium lead provenance signatures that evolved from the Oligocene through the Pliocene. And this project really came across as we were mapping the Indo-Burman fold thrust belt. We realized this was a fantastic place to study late Cenozoic tectonic climate interactions as they're recorded in these foreland basin deposits. So as mentioned here, the Indo-Burman ranges are located here just to the east of the Ganges-Brahmaputra Delta. The delta itself, the delta fan complex between the Ganges-Brahmaputra Delta and the Bengal and Nicobar fans is the largest depositional system on Earth. It is the result of the confluence of two of the Earth's largest rivers, the Ganges and the Brahmaputra, which of course drain most of the Himalaya. The white dashed line here shows the extent of the Ganges-Brahmaputra Delta watershed, with the Ganges River delivering sediment primarily from the Indian Craton and the frontal ranges of the Himalaya, and then the Brahmaputra watershed joining the Siang, crossing the Himalayan topographic divide, and connecting with the Yarlung watershed, delivering sediment to the Bengal Basin all the way from Tibet. And so together in the present day, these two deltas deliver over a gigaton of sediment per year to the Bengal Basin. And with recent work, particularly the IODP investigations 354 and 362, which produced large volumes of detrital zircon uranium lead data from the Bengal and Nicobar fans, it seemed like an ideal time to do a comprehensive investigation of detrital zircon provenance signatures that are preserved in the Indo-Burman ranges, correlate those with over a decade of work studying stratigraphy and provenance of the Eastern Sewalics, and then see if we can link that with source terrain data in the Himalayas, connecting this source to sink depositional system throughout the late Cenozoic, and providing maybe a framework for testing climate versus tectonic forcing mechanisms for the evolution of this basin. So this is the 1 to 4 million scale geological map of the Eastern Himalayas, which was published in 2001 by the Geological Society of India. Of course, we see then the Neogene foreland basin deposits of the Eastern Sewalics continuing around the syntaxis and connecting with the Naga fold thrust belt here in Arunachal Pradesh, Nagaland, Assam, and then leading into Manipur, Mizoram, and Tripura, which are the northeastern states of India that contain the Indo-Burman fold thrust belt. And so the deposits here in the Indo-Burman fold thrust belt are classically known as the TPOM group, which is really the late Miocene to Pliocene fluvial section. The Surma group, which is really a Miocene, mostly shallow marine succession, and then the Boreal group, which is a Oligocene, also fluvial deltaic succession. So throughout our structural mapping over the past several years, my first trip to the northeastern states was in 2015, working with colleagues in Mizoram at Mizoram University, as well as Government Satiri Residential Science College and Dibrugarh University in Assam. We have carried out several transects using road cut outcrops across the fault cord anticlines in the fold belt, and constructed this new lithofacies map of the Indo-Burman fold and thrust belt. And so I just kind of want to clue you into the color scheme here. The shades of pink and red are the TPOM group. This is the, again, late Miocene to Pliocene fluvial part of the ancestral Brahmaputra Delta, as I'll show you throughout this talk. The blue shades then are the Miocene Surma group, mostly shallow marine, deltaic, sandstone and shale. And then the purple shades are the Oligocene section, that's the Boreal group. That's a smaller delta that was draining the Eastern Himalaya prior to the arrival of the ancestral Brahmaputra River, which is really recorded by the Surma and TPOM groups. Okay, so keep that color scheme in mind. I'll be using that throughout the talk. So as we were mapping, we recognized that we needed to develop sort of a lithofacies scheme for identifying and correlating these formations across the structures in the fold thrust belt. And this was a study that was led by my colleague, Ryan Sienkiewicz, who's a professor of stratigraphy and sedimentology at Radford University. And he conceived that the simplest way to do this would be to use the lithofacies distributions in the modern Ganges-Brahmaputra Delta as a modern analog for interpreting the lithofacies that are preserved in really the Neogene Brahmaputra Delta in Mizoram and Tripura. And so we developed together with collaborators in Mizoram 3 lithofacies schemes for the fluvial section. That includes an F1 and an F2 facies, which refer to the fluvial tidal delta and interdistributary channels, and the fan delta and braid belt part of the modern system. So those are the fluvial part of the delta. and an F3 facies, which refers to the second cycle sediment that's eroded from the Indo-Burman ranges and Shlong Massif and then deposited on top of the delta. And if you're familiar with the Indo-Burman stratigraphy, you'll know the F3 facies as the Dupatilla group. And then we developed 4 lithofacies schemes for the shallow marine Surma group that represent different depositional environments on the modern delta. Starting from deep to shallow, the M1 facies are really the bottom sets of the subaqueous delta on the shelf. The M2 facies then are the 4 sets of that delta. The M3 facies are the top sets, as well as the intertidal and upper shelf deposits. And the M4 facies are the intertidal channels and distributary tidal channels that occur near the delta front. So using these lithofacies scheme, we were able to have some sort of semi-quantitative way of mapping throughout this massive clastic sedimentary system. So let's take a look at what this looks like in the fold belt. Here we're looking at pictures of the T-palm group. The 2 photographs on top show sort of the characteristic lithofacies that we call F1. These are meter scale, tan to brown, fine to medium sandstone with half-meter trough cross beds. And these are observed in a gradational contact with the shallow marine and intertidal deposits at the top of the Surma group. The bottom 3 photos then are of the F2 facies of the Surma group. These are massive meters to tens of meter thick tan to fine medium sand with meter scale trough cross beds and deep scours. And so these represent really the braid belt of the ancestral Brahmaputra River that have prograded what's now the Indo-Burman fold thrust belt back in the late Miocene and Pliocene. Okay, just for fun, here's a comparison of the scale of the trough cross stratification in the T-palm group, shown at the same scale with modern trough cross beds along the banks of the Jamuna River in Bangladesh. And so just by qualitatively noting the scale of the sedimentary structures that are present in these deposits, we can infer that this was indeed a massive braid belt river that had prograded the Indo-Burman ranges after 8MA. And then our lithofacies definitions of the T-palm group were greatly aided by contributions from my colleague, Dr. Zorm Thara. He goes by VZ for short. He finished his PhD on the sedimentology and stratigraphy of the T-palm group in Mizoram just in 2019, and now he's a professor at Government Zutiri Residential Science College. And so we were working together with VZ and another colleague who we'll introduce in a minute on defining these lithofacies schemes. So moving along to the Miocene, let's take a look at the 3 shallow marine lithofacies of the Surma group. On top here, then we see the M1 facies, millimeter to centimeter scale, planar laminated, silty shale, grading upwards into the M2 facies. The M1 then are interpreted as the bottom sets of the subaqueous part of the delta. The M2 facies are particularly distinct. Here we see these very strongly rhythmic, laminated, cyclical, 15 to 20 centimeter thick beds of fine sands and silts with unidirectional current indicators. We tentatively interpret these as the 4 sets of the subaqueous delta, but I've showed these photographs. You can see this very prominent pinstripe lamination going way up section here in the M2 facies. This is actually a quarry. This particular facies is mined for building stone, and so there are great outcrops of it. But this periodicity or this rhythmic patterns in the deposit here may also reflect something like tidalites or maybe annual or decadal signals such as perhaps monsoonal climate. So up section from the M2 facies is what we call the M3. These are centimeter scale light gray mud and siltstone with flazier and lenticular bedding, and these record subtidal to intertidal depositional conditions. And really most of the Surma group is dominated by the M3 facies. And finally, the top of the Surma group, we see meter scale massive sands with mixed trough cross bedding and bidirectional current indicators. And we interpret these as the intertidal channels of the delta. So on the lower left here, we see a nice continuous section grading up from the shallow marine subtidal conditions of the M3 facies through the intertidal section. And just off the photo to the left is the fluvial T-palm braid belt deposits of the F2. And we see that similar stratigraphic succession here in the photo on the right, with the M3 grading up into the bidirectional cross-bedded M4 channel deposits. And then all of that is prograded by the fluvial part of the delta represented here on top by the T-palm formation F2 facies. Okay. So this is a gigapan. Actually, if you click this link or go to this link, you can find this image and zoom in and see some detail across this continuous section of the upper part of the Surma group that we measured, or that Ryan measured, I should say, Ryan Sienkiewicz in 2018. This is a 400 to 500 meter thick stratigraphic column that continues from pro-delta depositional environments through the distributary mouthparts and interdistributary bays into the intertidal zone. And this whole section is capped by a gradational contact with the F1 facies of the T-palm group, which is the fluvial part of the delta. So we're really starting to make some progress in understanding sort of the different lithofacies that are preserved by this Neogene delta, and as well as their stratigraphic relationships with the T-palm group on top. Then below the Surma group is another group called the boreal group. The boreal group is almost exclusively, or as far as we know, it's exclusively Oligocene. And the boreal group represents an entirely different delta. And I'll tell you why with the detrital zircon uranium lead data in a few minutes here. But the boreal group on top, especially in the Naga belt in northern Assam and Arunachal Pradesh near the eastern syntaxis, the top of the boreal group contains thick coal seams, which are mined for heating and electricity. The shallow marine facies in the boreal group is mostly interbedded, tabular, 30 centimeter thick oxidized sand beds with siltstone and channelization. There's bioturbation and wavy ripple beds, all of the common characteristics of a shallow marine tidal environment. And then I just want to point out the picture on the bottom right. There are large infrastructure expansion projects in northeastern India, and there's new roads going in everywhere. And so, as you can see in this picture, there's just kilometers and kilometers of fresh outcrop through this Oligocene and Myocene sections that has never before been investigated. So it's just a really exciting time to go to the Indo-Burman ranges and really do some first order stratigraphy, structural geology, mapping, and understand the late Cenozoic Foreland Basin. Our understanding of the boreal group then was aided by our colleague, Dr. Lal Remruet Fella. He goes by Fella for short. He is a recent PhD also from Mizoram University, just like Dr. Zormthara. And he did his thesis on the sedimentology and magnetostratigraphy of the boreal group in Mizoram. And so he's probably the world's leading expert on the boreal group in Mizoram at this point, and it's been really a lot of fun to work with him and learn from him about this formation. Okay, so that's really an overview of what the deposits in the Indo-Burman ranges are comprised of, and I'm just going to move right along and tell you about what we know about their depositional ages and sediment accumulation rates, thanks to some recent magnetostratigraphic studies that were carried out by colleagues at Mizoram University and Zutiri Residential Science College. And so I'll show you sections, one section from the T-palm group, one section from the Surma group, and one section from the boreal group from these PhD theses. So fellow, or Dr. Lal Remruet Fella's PhD dissertation, as I mentioned, was on the boreal group. Here we can see his measured sections covering, over a kilometer of section here, and spanning the magnetostratigraphic interval starting at the bottom of the Oligocene and going right up to the top of the Oligocene near the Oligomycene boundary. And from this section, then, he has calculated sediment accumulation rates on the order of about, between maybe 25 and 40 or so centimeters per 1,000 years. So this is the really first high resolution chronostratigraphic investigation into the boreal group that's matched with lithostratigraphic logs. And it's a really nice contribution to our understanding of the Indo-Burman ranges. So if you're interested in this, I encourage you to check out his dissertation. It's available online through the Missouri University Geology Department website. So I want to point out then that the top of the boreal group here really only extends up to about 24 or maybe 23 MA. Okay. Well, a companion paper that was published a few years earlier. This is a 2010 Geological Society of India publication looking at the stratigraphy and magnetostratigraphy of the Surma group. This is by Dr. Malswama, who is also professor at Missouri University and has introduced us to some very nice outcrops of the Surma group, in particular the one I showed you in the Gigapan photo a few slides ago. So they're measuring two sections here through the Surma group. The lower Surma group stratigraphic section spans from about 21 MA up to about 15 MA. And later in the talk, I'll refer again to this Turial section. This is a section from the middle to the upper Surma group, which spans the interval from about 12 or 13 MA up to about 8 MA. And this section is particularly important because this is where we transition from the M3 facies, the upper shelf deposits, into the intertidal zone. And here they document this doubling of the sediment accumulation rates from something on the order of 20 to 25 centimeters per 1,000 years up to 40 to 50 centimeters per 1,000 years. So we're seeing this upsection increase in the sediment accumulation rate through the Myocene Surma group up until about 8 MA. And then there was another PhD by Dr. Lal Nulanga. These Mizo names are a little difficult for me to pronounce, but I practiced. And he did his PhD on the T-Palm Formation in northwestern Missouri. So this is probably the top of the T-Palm Formation, and it's certainly the youngest part of the deposit that I'm aware of. So the magnetostratigraphic column through the upper T-Palm Formation then places it in the Pliocene between about 4.6 to 3.3 MA. And he's documenting here sedimentation rates upwards of a meter per 1,000 years. So we see again an increase in the sedimentation rate from the top of the Surma group into the fluvial part of the delta that's recorded by the T-Palm group. Okay, so since we have this background magnetostratigraphic columns through our sections, we can use them to evaluate some of the maximum depositional age analyses that we have attempted in the Indo-Burman ranges using detrital fission track thermal chronology. And I need to point out that all of the new thermal chronology and geochronology analyses that I present in this talk and in our papers were carried out by Stuart Thompson at the University of Arizona. Okay, and so then the first 5 data sets you see here, these are radial plots showing the single grain ages of a population of fission track grains, sample sizes on the order of 100 grains per sample. And we're fitting then using radial plot, which is a Peter Vermeesch statistical program, where we're doing a statistical fit to the minimum age, the minimum peak age in the distribution. And then since fission track records really the last time that this grain passed through the partial annealing zone, it's then recording a cooling age or an exhumation age of the source terrain, because these are on-reset populations. In other words, the single grain ages spanned a wide range. And so we have to account for the lag time. And the lag time is the time that transpires between the cooling age of the grain and the time that it is eroded at the surface and deposited in the sedimentary basin. So by comparing our minimum age models from the T-Palm Formation to the stratigraphic age at the top of the Surma group, this is T-Palm Formation collected just above the gradational contact between the T-Palm and the Surma group. The top of the Surma group is 8 MA, and our minimum age models are on the order of 13 or 14 MA. So that requires a detrital zircon fission track lag time on the order of 5 ml. So by using this lag time, then we can estimate maximum depositional ages of the T-Pump formation and help to improve our understanding of the age of these units throughout the Indo-Burman ranges where we don't have magnetostratigraphic data yet. So doing a similar exercise then, we have 2 new samples from the middle part of the Surma group. These samples were collected from part of the section that correlates with the lower part of the Tui Real magnetostratigraphic section that I just showed you a few slides ago. The magnetostrat age for that section is 12 MA, and our minimum age mixing models for the DZFT data here is 22 MA, and so that requires a lag time of 10 million years. And so the implication here then is between the top of the Surma group and the TPOM group, we have a decrease of lag time by a factor of 2, which means an increase in the erosion rate of the source terrain by a factor of 2. And that reflects more rapid sediment supply to the delta and higher rates of erosion in the Himalaya. And I'll come back to this later in the talk. This isn't a crazy result. This is something that's actually been documented in the Eastern Syntaxis by other researchers. And then finally, going back to the Boreal group, looking at our minimum age models, we've got ages of 33 and 34 MA, and using a lag time of 10 MA, that brings them back to a maximum depositional age of 23 or 24 MA, which matches the magnetostrat age of the Boreal group at the top of the formation where these samples were collected. So we're seeing then the take-home message from the DZFT is a doubling of the erosion rates as reflected by a decrease in the lag time by a factor of 2 between the top of the Surma group and the top of the TPOM group. Okay, so we kind of wrapped up this paper then with an interpretation of the progradation of the Surma and TPOM groups, which I'll show you in the next part of the talk, reflects the progradation of the ancestral Brahmaputra Delta. On the left-hand column, we see some, this is QT. That's a thermal modeling program by Kerry Gallagher that uses Bayesian statistics to predict the heating and cooling pathways of a sample based on various types of thermochronology data, including, in this case, apatite fission track and apatite helium results. So by imposing temperature and time constraint for the maximum depositional age, the model predicts burial reheating until about 6 or 7 MA, followed by steady state or maybe punctuated exhumation up until the present day. And so we think that this reflects really burial during progradation of the delta until about 7 MA, and then the onset of exhumation in the Indo-Burman fold belt starting about 6 or 7 MA. And that's consistent with some other work that's been published by Yanni Nyman and others who predict, also using detrital thermochronology methods, that the propagation of the deformation front of the Indo-Burman ranges had pushed the Brahmaputra Delta to its present course north of the Shillong Massif. And so that great effulsion of the Brahmaputra Delta is really something that's occurring in the late Miocene and into the Pliocene. And we think that's also reflected by our thermochronology data here from the Surma group. Okay, so that was our introduction to the stratigraphy and thermochronology and magnetostratigraphy of the Indo-Burman ranges, mostly in Mizoram and also Tripura. And this led us to our second paper that I'm going to talk about today, which uses detrital zircon uranium lead data to attempt to quantitatively correlate deposits of the Indo-Burman ranges with more proximal deposits in the northern Indo-Burman ranges, as well as the eastern Himalayan Siwaliks, and then use those correlations to try to understand the evolution of the ancestral Brahmaputra watershed, how it integrates with the Songpo watershed, and eventually it results in the delivery of Tibetan sediment to the Bengal Basin. And so this paper, we present really 12 new high-end detrital zircon uranium lead data from the Boreal, Surma, and TPOM groups in the Indo-Burman ranges. And then we present compilations from the literature from numerous sources. You can find all the sources in the paper. I don't have space to put them all on the slide, and compare that data then with compilations of bedrock, zircon, uranium, lead data from the Himalaya. Okay, so let's take a look at the data sources that we're comparing with the Indo-Burman ranges. Here we see several studies in the Eastern Himalayas Sewalics that were carried out really since the earliest is 2009, Saracena and others, along several river cut transects that cross the Sewalic group in the Eastern Himalaya. That's Pasighat, Remi, Likabali, Tanagar, and Balukpong transects, as well as a few others that are off the map to the west in Bhutan and the Sikkim Himalaya. Okay, and then we compare that data with our new IBRDZ data here from the Indo-Burman ranges in Mizoram, as well as previously published IBRDZ data from the Surma Basin here in Bangladesh and other locations here in the Naga fold thrust belt to the north. All right, so now that we have a new magnetostratigraphic and zircon fission track constrained depositional ages for the Indo-Burman stratigraphy, we can correlate them temporally with previously published work in the Eastern Himalayan Sewalic, and we find that the TPOM group of the Indo-Burman ranges, the contact then between the TPOM and the Surma group is 8 Ma. That corresponds really with somewhere in the middle part of the middle Sewalics and continues up section all the way to the end of the Pliocene and the top of the middle Sewalic group. So these massive braid belt deposits of the TPOM group are correlative in time and lithofacies with similar deposits in the middle Sewalics of the Eastern Himalaya. And then the Surma group correlates with the lower part of the middle Sewalics in time, as well as the entirely or all of the exposed section of the lower Sewalics in the Eastern Himalayas. One reason to study the Indo-Burman stratigraphy is because the Indo-Burman stratigraphy preserves the Oligocene section, which does not crop out in the Eastern Himalayan Sewalics. So if we want to look at tectonic and climate forcing mechanisms in the detrital record across this late Oligocene to Miocene boundary, we need to go to the Indo-Burman ranges because we're not going to find those rocks in the Eastern Himalaya Sewalic group. And so this stratigraphic boundary between the Boreal group and the Surma group in the Indo-Burman ranges is about 15 to 18 Ma based on the oldest DZFT data in the Surma group. And then we know from magnetostrat, the top of the Boreal group is about 24 Ma. So either we have some older part of the Surma group, I think some of the magnetostrat data gets as old as 20 Ma that isn't well exposed in Mizoram, or there's an unconformity and depositional hiatus between the Boreal group and the Surma group. And unfortunately, this contact is quite recessive and not very well exposed. And so on a number of attempts, I haven't really been able to put my hand on it and say one way or another. But nonetheless, the onset of the Surma group, true blue Surma group in the Mizoram part of the Indo-Burman ranges occurs somewhere between 15 and 18 Ma. And that brings us back to the oldest part of the Sewalic section that's exposed in the Eastern Himalaya. Okay, so I'll first show you the Basin detrital zircon uranium lead data from the Indo-Burman ranges. We'll compare that with the same from the Eastern Sewalics, and then we'll use that to compare with various Himalayan source terrains. And so we also went through the literature and made large N compilations of the detrital zircon uranium lead data from the Himalayas, which is presented here. And again, this is largely me just compiling data from the supplemental files of lots of previously published papers. I don't have the whole list of references here, but you can find it in our paper if you're interested to see where all this data comes from. And so if you're familiar with DZ uranium lead dating, this might look quite familiar to you. And if you're not, I'll just say we can use, these are kernel density estimates showing the relative proportion of populations of zircon uranium lead grains from various possible bedrock and the modern Brahmaputra watershed, as well as the modern Ganges watershed compilations. And so the peaks here are showing populations that are unique to each of these different Himalayan source trains, including the Lhasa train, the Tethyan Himalayan, and the upper Lesser Himalayan series, the Greater Himalayan series, and the Lower Lesser Himalayan series, as well as the Shillong Massif and the two river profiles that I just mentioned. So by looking at the basin data, then we can identify different age populations that correspond to some of these peaks and use statistical methods to determine what proportion of each of these Himalayan terrains is contributing sediment to the delta. And then I want to emphasize the younger part of the population here, that grains less than 300 MA generally belong to the Ganges Arc, which is the plutonic roots of the volcanic arc that was formed when the Tethys Ocean subducted beneath the Lhasa terrain. And this is a unique signature that only occurs in the Brahmaputra watershed. So this less than 300 MA population is only present in sediment that was delivered from the Sangpo River across the Himalayan Divide and into the Himalayan foreland. And so that's a unique signature of a Brahmaputra-derived section. Okay, and it's not present in the Ganges because the Ganges watershed never crosses the Himalayan Divide. And so we don't bring sediment from Tibet down the Ganges River. Okay, so let's take a look then at the basin data. These are showing, these are ordered according to the stratigraphic column from bottom to top. Okay, the TPOM and middle Sewalics then are correlated at 8 MA with this arrow here. In between is the Surma and the lower Sewalics. And of course, we don't see the Oligocene in the eastern Sewalics, so we only have that record present in the Indo-Burman ranges. And it's a good thing because that contact between the Boreal group and the Surma group is where we see the most significant change in the detrital zircon uranium lead provenance signature of sediment coming into the Bengal Basin. So all of the samples contain age populations that can be correlated with various Himalayan source trains, but only samples in the Surma group and the TPOM group contain sediment that has a significant proportion of that Ganges arc signature, which indicates that there was not any significant trans-Himalayan watershed established until the Surma group or until the early Myocene arrival of Surma group and TPOM group sediment to the Bengal Basin. And so that's why we refer to the Surma and the TPOM group as the ancestral Brahmaputra Delta, because during the Oligocene and Boreal time, that watershed had not yet established a trans-Himalayan source and was probably just sampling sediment from the eastern syntaxis or the Bomichara batholith, which I'll come back to in a little bit. So let's just take a look at that data. These are cumulative density functions, cumulative distribution functions, excuse me, showing the relative probability of grains of certain age sorted by age. And so then a steep step in this plot represents a population of grains, a strong population of grains of a corresponding age. And so coloring these qualitatively by time, yellow is the Oligomycene, kind of green-blue is the Miocene, and then blue is the Myopliocene. We see this very nice upsection trend from the absence of Ganges arc-derived sediment and that sediment then occurring in increasing proportions up through the Surma and the TPOM group in our new data from the Mizoram part of the Indo-Burman fold belt. So then I started to dig into the literature and compare this with previously published data from the Surma Basin in Bangladesh, as well as the Oligocene and Miocene section that's exposed in the Naga fold and thrust belt. And we can see very similar trends where we see the systematic upsection increase in the relative proportion of this less than 300 MA population. And just qualitatively here, by comparing these trends, we see that that less than 300 MA population is really the population that separates the three stratigraphic groups. They have very similar trends looking at the Proterozoic age, zircon age spectra. So it's the Ganges arc proportion that defines the provenance shifts up section. Okay, So now we're compiling here, maybe 10 years of work in the Eastern Sewolics, and I've pulled all the papers I can find that have DZ uranium lead data from age equivalent deposits of the Eastern Sewolics. So starting with the easternmost parts of the Eastern Sewolics, these are papers by Carl Lang, Gladys Goldman, and Gianni Najmi group. They're really showing only sediments that are maybe no older than 12, or I think the oldest one here is 13 MA. And all of these middle to late Miocene sediments contain a significant portion, either 10 to 20% or more, of Ganges arc grains. So here, like in the Indo-Burman ranges, these correlate in time with the Surma group, the upper part of the Surma group, as well as the TPOM group. These sediments are also receiving those grains, which makes a lot of sense because this is in a more proximal position than the sediments that we were looking at in the Indo-Burman ranges. So if we move along to the western part of Arunachal Pradesh and we look at the Itanagar and Balakpong section, we see similar trends where both the Itanagar and Balakpong middle to late Miocene sections here in blue and green contain this Ganges arc DZ signature. However, going farther west, some work by Saracena, 2009, all the way to Sikkim shows that DZ signature was never present in the Sikkim part of the Himalayan foreland. And so there's a westward extent to which we have trans-Himalayan sediment delivered to the Sewolic Basin. Between Sikkim and the Balakpong section is a relatively new section that was studied by Gladys Goldman and Yanni Unaiman and others and published in a geology paper 2018 in Bhutan. Here things get a little more nuanced where even the late Miocene section does not record any of the Ganges arc signature. However, that signature does appear later in the stratigraphy in the Pliocene part of the section. And so this group published a nice paper in geology where they used this data set to show that the Brahmaputra River had avulsed from delivering sediment to the Indo-Burman ranges in the Miocene and early part of the Pliocene. And by the Pliocene, it had avulsed to the north and west of the Shillong Massif along the Himalayan foreland here in a course that looks much more like its modern course, where it joins the Ganges and then delivers sediment to the Ganges Brahmaputra Delta. Okay, so there's a little extra nuance there in the Bhutan Sewolics, recognizing that the Ganges arc signature doesn't appear until the Pliocene. So I correlated these along strike using the magnetostratigraphic and columns that have been published in many of these papers, and I made large and detrital zircon compilations of similar age data. So we have two Miocene populations, one reflecting stratigraphy younger than 8 MA and one reflecting stratigraphy between the time period of 12 to 8 MA, which correlates in time with the middle to upper part of the Surma group. And then this younger one here correlates in time with the TPOM group. And it's these two populations that really record this influx of Ganges arc signature grains to the Bengal Basin, whereas the older and farther west deposits look much more like the modern Ganges watershed, which is plotted there in the thick red line. And then the Miocene and late Miocene to Pliocene deposits trend toward the modern Brahmaputra watershed, which is plotted with the thick blue line. Okay, so by compiling the data from the Indo-Burman ranges for equivalent time periods, that's the Boreal group for the Oligocene, which again is not recorded in the Eastern Sewolics. The Bokabille and the Buban formations make up the Surma group, and then we have the TPOM group. I can match those to our less than 8 MA and 12 to 8 MA populations from the Eastern Himalayan Sewolics. And we can see then that, at least qualitatively, the DZ uranium lead age distributions look very similar. For the 12 to 8 MA Sewolic section is a very good match to the TPOM group. And the less than 8 MA Sewolic section then is a very close match to the, sorry, I misspoke. The 12 to 8 MA Sewolic section is the Surma group, and the less than 8 MA Sewolic section is a very good match to the TPOM group. And so just using some statistical tests to match these, here I'm plotting these two compilations of this is 8 to 3 MA Sewalic DZ uranium lead data in the solid line. And right below that, you can barely make out the dashed line. That's the IBR TPOM group compilations of the same age. And we can see they're a nearly perfect match in terms of the detrital zircon uranium lead signature, giving a cross correlation coefficient of 0.8, which I think is pretty impressive for this type of data. Similarly, if we're looking at the 12 to 8 MA Eastern Sewalic group and comparing that with the Surma group in the Mizoram and Tripura part of the Indo-Burman ranges, we get very good 0.7 cross correlation coefficients between these two distributions. So taking these two compilations, the Sewalic and Indo-Burman data set, I just put them together again because they're practically identical and made regional Indo-Burman Sewalic compilations that show the systematic trend in the change of the provenance of the Indo-Burman sediment coming from the Himalayas. And that change then is recorded by this increase up section in the relative proportion of trans-Himalayan arc grains, which drive the sediment from a more Ganges-like watershed to a more Brahmaputra-like watershed through time. And then here in the purple line, I'm just plotting the younger Plio-Pleistocene Bhutan Sewalic section, which is showing the later arrival of that Ganges arc-derived sediment after the avulsion of the river north of the Shillong Massif. Okay, so using the DZ uranium lead data, then we can make very convincing quantitative stratigraphic correlations between the Eastern Sewalics and the Indo-Burman deposits. Okay, well, let's plot this data a little differently. Here we're looking then at a multidimensional scaling plot. The X and Y axes on this plot are a dimensionless factor, which just gives you the similarity between two data points. So this is much like a principal component analysis, where here we're just plotting the two most significant parts of the IBR, or excuse me, of the DZ uranium lead populations and looking at the similarity or dissimilarity by evaluating how closely they cluster on our diagram here. So the Ganges River compilation is plotted in red and the Brahmaputra River compilation is plotted in blue. And here we can see these dashed lines separating data from the different parts of the IBR stratigraphy. And we see this nice systematic trend up section from the Brau group, which is really a frontal Himalayan watershed, collecting increasing components of trans-Himalayan sediment and trending toward a trans-Himalayan watershed or Brahmaputra-like watershed by the time we get to the upper Sewalic and TPOM group deposits. Okay, so then we can do a few more little fancy statistical techniques. We can take the compilations of the known bedrock source terrain data. So these are bedrock uranium lead data sets. And we can produce, thousands of random mixtures of these data sets using inverse Monte Carlo modeling methods that have been incorporated into this really nice piece of software called DZ-Mix by Kurt Sandell and Joel Saylor. It was published in 2017. This is open source software. Anybody can download and use it for free. And we'll keep the best fits here that are the best match to the basin data. And we can test then for trends through time in the relative proportion of different Himalayan source terrains that are contributing sediment to the Indo-Burman basin. And so really here, just by comparing the main Himalayan terrains with the Boreal, Buban, Bokabil, this is the Surma group, as well as the TPOM group, we see this nice systematic upsection trend in the trans-Himalayan arc population. These are less than 300 MA grains coming from the Ganges batholith. We see an upsection trend in the proportion of sediment coming from Lhasa terrain, and that is occurring at the expense of sediment coming from the Himalayan foreland in the greater Himalayan, Tethyan Himalayan, and lesser Himalayan series rocks. And so this is reflecting then this temporal trend upsection from a frontal Himalayan watershed in Oligocene time through the Myocene to a distinctly trans-Himalayan or modern Brahmaputra watershed by the late Myocene and Pliocene time. Okay, we can do the same inverse Monte Carlo exercise with the modern river compilations as possible source terrains instead of the bedrock compilations. So here we're just comparing either the Ganges watershed contribution population with the Brahmaputra watershed population. And so the model is forced to pick one or the other, so don't pay any attention to these relative contributions. The more important thing to look at is the fit statistics. And so as we go up section from the Boreal for the Surma group to the TPOM group, we see increasing relative contributions of the Brahmaputra Lake watershed, shown in blue, and the fit statistics don't become acceptable until we see this really Brahmaputra-derived watershed. So what this means is there's really no Ganges sediment in the Indo-Burman ranges, and moving upside, at least the modern Ganges, there's some issues there that the Paleo Ganges might not have looked the same, but nonetheless, as we go up section to the TPOM group, we get more of a true trans-Himalayan watershed. Okay, so since the trans-Himalayan arc population is the most important part of the distribution, let's take a minute and then just look at the DZ uranium lead signatures of the less than 300 MA part of this distribution. And we can compare that with our new paleogeographic reconstructions of the Eastern Himalayas from the late Oligocene and through the Miocene. So now we're looking at Boreal time. The Boreal was a delta of smaller size and magnitude than the Surma TPOM delta, but nonetheless, it persisted up into the corner of the syntaxis. There's shallow marine deposits that are recorded in the sedimentary record well into Assam. And we also see nice terrestrial coal beds at the top of that section in the northeastern part of Assam. And so looking at the DZ signature plotted here in orange, dashed orange line, the Boreal group more closely approximates the DC signature of the Bomi-Chaya batholith, and it lacks a significant proportion of 50 MA grains that are really characteristic of the Ganges batholith, as well as the Eastern Himalaya and Nanche bedrock terrains. And so we think then during Boreal time, during the Oligocene, this was a relatively local frontal Himalayan watershed, perhaps feeding sediment down maybe the Parlung to the Lohit River into the Boreal Delta. And then by the time we get to the early Miocene, and certainly by the middle Miocene, when the Surma group is going full force, we start to see this influx of 50 MA grains that record integration of the ancestral Brahmaputra River with the Yarlung watershed, and is unequivocally delivering sediment of the Ganges batholith in Tibet, as well as the Lhasa terrain, to the Indo-Burman basin. And so the Surma Delta then is recording progradation of what we might call then the ancestral Brahmaputra Delta after expansion of the Brahmaputra watershed into the Yarlung watershed. And I just want to highlight a very nice paper by Zhang and others published in 2019 in Earth Science Reviews, who gives an even deeper time interpretation of the evolution of Eastern Himalayan rivers, going back to the Eocene, showing the transition from Yarlung to Red River sediment delivery through the Irrawaddy into the Lohit, and then into finally the Brahmaputra River. And if the authors are here, I meant to cite this in our paper, and I didn't, and I apologize for that. That was simply an oversight on my part. But I'd like to point the audience to that paper to look at another nice example of watershed reorganization in the Eastern syntaxis. Okay, so I'm going to try to pick up the pace a little bit because I think we're running out of time. But the next thing to do then is to compare the Indo-Burman range DZ uranium lead data with new data that has been produced by the IODP investigations of the Bengal and Nicobar fan. And so this is an interpretation of patterns of sediment delivery to the Bengal and Nicobar fan from the Indo-Burman ranges. And so here, this topographic high we see, this is the 90 East Ridge. To the west of the 90 East Ridge is the Bengal fan. To the east of the 90 East Ridge is the Nicobar fan. So through the Oligocene, we have primarily sediment delivery along toward maybe what you might think of as the ancestral Nicobar fan, going along the trench. This sediment, this Oligocene sediment, is accreted in the forearc high that defines the modern day Andaman Islands. And where things start to get interesting is really in is in the early to middle Miocene, where we start to see sediment delivery to both the Bengal fan and the Nicobar fan, and maybe some lobe switching or alternating pulses of sediment delivery between the Bengal fan and Nicobar fan occurring in the late Miocene. So let's take a look at some of that data and compare it with the Indo-Burman IBR Sarawak DZ compilations. On the bottom here, we'll start with the Nicobar fan. This is a nice paper published by Pickering et al. In 2020 that presents really the DZ record that was produced by IODP 362. And here we can see the Nicobar fan wasn't really receiving much sediment through the early part and really all the way up to the late Miocene until about 9.5 MA, where all of a sudden the mass accumulation rates on the Nicobar fan spike up to about 45 grams per centimeter squared every 1,000 years. And that mass accumulation rate remains relatively high until about 5 MA, where there's a brief hiatus, then it picks up again, and then it stops right here at the end of the Pliocene. So if we take a look at this Nicobar fan data, that's a solid yellow line. The oldest part of the data here really is quite similar to the Boreal group. And so we're not getting any trans-Himalayan sediment to the Nicobar fan in this oldest part of the section. But then Nicobar fan sections 2, A, B, and C, are all very self-similar, and they trend almost exactly according to the DZ uranium lead signature of the Surma group in the Indo-Burman ranges. And the Surma group then is, of course, older. The Surma group is 12 to 8 MA in this data set, and our Nicobar fan compilation starts at 9 MA when the mass accumulation rates increase and continues through the Pliocene. So it's obviously not recording the same sediment because it's not the right time period, but it is certainly recording an influx of trans-Himalayan arc sediment to the Nicobar fan starting at 9 MA. And I think that's significant because 9 to 8 MA is a stratigraphic transition between the Surma group and the TPOM group. So it's probable then that purgation of the fluvial part of the delta, that's the TPOM group in the Indo-Burman ranges, is delivering sediment directly to the Nicobar fan, and that might help explain this large step in mass accumulation rates at that time. Okay. Well, we can then look at the Bengal fan. Here we're showing the mass accumulation rates for the Bengal fan in green. The Bengal fan really started to pick up sediment right here about 14 MA, and that sediment supply remained relatively high through the late Miocene and into the Pliocene, then it died off again, and then it spikes again quite recently in the Pleistocene. And so if we look at our Bengal fan DZ uranium lead compilations, the oldest part is again quite similar to the Boreal group or the Ganges watershed compilation. And then starting in the late Miocene from 12 to 8 MA, we get an influx of trans-Himalayan sediment that matches in time approximately with this increase in mass accumulation rate and the Bengal fan. And then it decreases again, starting at about 8 MA for 1 million or 2 years. And we see less trans-Himalayan sediment delivered during this interval in the late Miocene, which perhaps reflects the fact that the TPOM group at that time is then delivering sediment to the Nicobar fan, and the Bengal fan's not getting as much of that trans-Himalayan signal. And then by the Pleistocene section in the Bengal fan, we see this big spike in trans-Himalayan arc sediment coming into the fan at that time, and that reflects the avulsion of the Brahmaputra River along the Shillong Massif, where it joins the Ganges and delivers sediment and then to the Bengal fan. So that's really the compilation of data that I've put together over the past couple of years and presented in our papers. And now I just want to, for a couple of slides, ask some questions. And then the obvious question is why, and what is causing this large step change in the provenance and watershed reorganization in the Eastern Himalaya across this Oligocene to early or middle Miocene stratigraphic boundary. Okay, so what causes a step change in a huge depositional system the scale of the Brahmaputra River and the Bengal Basin? Well, it's probably going to be either climate forcing or tectonic forcing. And so it would be worthwhile then to take a look at some of these hypotheses. So we'll start with tectonic forcing. Here is a figure from Laskowski and others, and this is really an ongoing work at University of Arizona. There have been a number of papers published here looking at the Ganges thrust system near the Yarling Sangpo Suture in southern Tibet, which is separating, Indian-derived terrains from the Lhasa terrain, and the Ganges Mountains, right, the Ganges Arc. And so they document a period of early Miocene uplift and exhumation, which is attributed to activity on the Ganges thrust, as well as larger scale geodynamic processes, such as maybe slab rollback and slab breakoff below the southern Tibet, that is recording really tectonic uplift and the creation of topography in central Tibet here, and has been hypothesized to cause the reversal of the Yarlung River toward the east, which then, of course, in the early Miocene is the right timing for delivering Ganges sediment through the Yarlung to the eastern syntaxis and eventually to the Brahmaputra watershed. So this is early Miocene tectonic activity in the hinterland of the Himalaya could be helping to drive Tibetan sediment into the Bengal Basin. And then again, if we go along strike to the east and look at the eastern syntaxis, this is a map of the Namche Barwa Massif in the eastern Himalaya, which is transected by the Siang River, based on some compilations of multi-system detrital thermochronology that were published by Gladys Govan and others in 2020, and several other workers before them. We know that the erosion rates in the eastern syntaxis in 2MA have been extremely high, on the order of 9 millimeters per year, which is 10 kilometers of exhumation per million years since the Pleistocene, right? And this new paper then documents really an increase in the erosion rate up to 4 millimeters per year at 8 MA, based on a decrease in the lag time of these multi-system thermochronometers from 10 million year lag times to something on the order of 4 or 5 million year lag times. And so this 8 MA decrease in lag time that's recorded in sediments in the eastern Sewaliks here, this is exactly what we see with our decrease in lag time between the Surma group and the TPOM group, also at 8 MA, farther downstream in the Indo-Burman ranges, which I mentioned toward the beginning of the talk. And so there's clearly some feedback between, indenter corner dynamics here, where India is colliding with the corner of the eastern syntaxis and driving deformation and vertical rock advection toward the surface, feedback with rapid rates of incision in the Siang River that help to deliver increasing proportions of trans-Himalayan sediment to the Bengal Basin. But then I also think it's extremely interesting to think about climate forcing mechanisms, which is more related to topics of interest for people in this session, and really point out the fact that it's quite enticing that the timing of this step change in the provenance shift between really frontal Himalaya or eastern Himalaya drive sediment going into the Boreal group to trans-Himalayan drive sediment that comprise the Surma and the TPOM groups of the ancestral Brahmaputra Delta. While the beginning of that Surma group is really 18 to 15 MA, which overlaps with the Miocene climate optimum and hypothesized onset and intensification of the South Asian monsoon. So maybe our increase in denudation and erosion rates is reflecting increasing denudation of the high Himalaya during the intensification of monsoon conditions, and this sort of long-term first-order progradation of the ancestral Brahmaputra Delta is reflecting global sea level fall after the Miocene climate optimum. And so, these are questions that need further investigation. And so I'll just finish here with a few take-home points. So Tibetan sediment first appears in the Bengal Basin with the Surma group in the early Miocene. This records the ancestral Brahmaputra drainage integration with the Yarling Sangpo watershed. Sediment from Tibet increases up section through the late Miocene to Pliocene TPOM group. This change, a step change in the provenance of sediment coming to the Bengal Basin, could reflect both tectonic and climate interactions in the internal part of the Himalayas. So future paleoclimate proxy and chronostratigraphic studies of the Indo-Burman ranges are needed across this transition from the Boreal group to the Surma group to test these hypotheses. And of course, then this is important. Maybe this is the most obvious part, but also the most important. Filling of the Bengal Basin because of extreme sediment supply from the Himalayas has created the world's largest example of subduction accretion, which is presently home to over 200 million people who live on this four-arc accretionary prism. And that's what really is driving my research here. And it's been interesting to think about this late Cenozoic evolution of the Foreland Basin. And so finally, I've got lots of people to acknowledge. Here are my colleagues, VZ and Fella, who work on the TPOM and Boyle group stratigraphy and sedimentology at the University of Mizoram and Government Zitiri Residential Science College. When we go and do field work together, they often arrange short courses, field short courses, or even we had a 2-week field school back in 2016, where we take students from Mizoram University and Zitiri Science College out to the field, and we do structural geology transects across the fold belt. And also more recently, since I started here at George Mason, I've been able to bring my own students. This is Kristen Kiyama, who is an undergrad at George Mason, did a senior thesis project with me in the Indo-Burman ranges. Here's Ryan Sienkiewicz, who did the stratigraphy with VZ, and then Ryan's student, Lucas Rimanelli from Radford. And this is a recent PhD from the University of Dibrugarh. His name's Raghu Pratham Rakshit. He's working on the neotectonics of the Indo-Burman ranges and is now teaching geology courses at PUC College in Mizoram and is seeking postdoc opportunities. So it's really just been a wonderful time to interact with the students and develop these collaborations over the past few years of this project. So thanks very much for listening, and I'll welcome any questions.
Great, thank you so much for a wonderful talk. I see that we already have a couple of questions in chat. And I think you might have answered the first one, but I will ask Vitali, do you want to read these out yourself, or would you like me to read them out for you? Okay.
I'm good, thank you.
Would you like to read them out? This is so that people who are in YouTube, for example, can't see the questions, so that they can see which questions are being asked.
Yeah, no problem.
So would you like to ask your question? So just read out what you've written?
You can ask, yeah.
Oh, okay. So Vitali first asks, which I think you've explained just shortly, was how would you explain the increased sedimentation in the TPOM group, but over 3 to 4 million years?
Well, I think, there's a couple possibilities that I mentioned at the end of the talk. We certainly have an increase in the erosion rates in the eastern syntaxis starting at 8 MA, which would then be increasing the sediment supply to the Indo-Burman ranges right there at 8 MA, which is the beginning of the TPOM group. And that erosion rate continues to increase from 4 millimeters per year at 8 MA to 9 millimeters per year at 2 MA. So that's one possibility. And then the other possibility would be intensification of monsoon conditions in the Eastern Himalaya might increase rates of erosion and sediment flux to the Bengal Basin.
Okay, I got you.
And then there's another question. And then I was curious about this as well, since you didn't really talk about this directly, so how did essentially Indo-Burma collision change the sedimentation, or what would you envisage for that?
I asked this question at the beginning or in the middle of this presentation, so yeah.
Yeah, okay. So Indo-Burman collision, are you referring then to the collision between India and the Burma terrain, or
I
India
mean,
and
with
the
all this subduction zone and IBR rising?
Yeah, yeah. Well, there's two periods. There's a couple papers on this topic from the Najman group working here in the western ranges of Myanmar, and also a group by Alexei Licht and others working on sort of magnetostratigraphy or paleomagnetism from the Burma terrain. And there's really two periods of collision. So the first is the Eocene, which is the collision of the Burma terrain with the Indian margin, and then the second is in the Oligocene, which is the collision of the Indian margin and the Burma terrain together with the Eastern syntaxis. And so that first period we don't see in the data that I'm showing because it's Eocene, and we're just looking at the Oligocene through the Pliocene. But that second collision then in the Oligocene could be recorded by sedimentation in the Boreal group as the Burma and India, the Burma microplate and India are moving northward together into the Eastern syntaxis. And so, maybe we can speculate that this Oligocene collision is persisting and perhaps affecting the dynamics of the indenture corner through the Miocene to the present day. I mean, there's still active tectonism along this plate boundary. So does this answer your question?
No, I'm okay. I just would like to read these articles you mentioned.
Okay, sure.
So I had a question somewhat related to that with collision. So do you find any change like within your data sets with the change in obliquity at all in collision? And I don't know if maybe any changes in, like, let's say lateral accretion or vertical accretion with the development of the central Indo-Burman ranges throughout all of this. I know that there's a really strong signal obviously coming from the river, but I was curious if there was any type, I don't know, reworking signal that could be picked up from your data set or data sets.
Yeah, that's a good question. So, the obliquity of the collision, this is a highly oblique subduction zone. The obliquity is 70 degrees. And so the convergence is north 20 east, and the plate boundary is about north south. And so structurally, at least in the modern, and then going back into the Miocene, looking at reconstructions of the fold belt, we can see that that's pretty strongly partitioned. So the anticlines strike north-south, and they're propagating westward and really absorbing the eastward component of this oblique collision only. And then the northward component of the obliquity is taken up by the Churchampo fault and the Sagaing fault in Burma, as well as possibly along the Cabal fault here, which separates the Indo-Burman ranges from the central Burma basin. So in that sense, the strain is pretty strongly partitioned. Now, in terms of what I think you're getting at, which is the depositional record of the development of and propagation of the fold belt through this oblique forearc, I didn't really mention it, but if I can just skip all the way back, I know you're not supposed to do this, but I'm going to do it anyway, to our data, we do have one outlier T-palm formation maximum depositional age in the middle Miocene, and that's from a minimum peak age of 20 MA, and then applying a short lag time. And that sample is taken way up here in the northern part of the Naga Belt. And since this is a delta that's prograding across the whole Miocene, Pliocene time period, then we expect sort of equivalent, this is a time transgressive system, so we expect older T-palm facies in the northern part of the fold belt than we do in the southern part of the fold belt. So here we've got this kind of middle Miocene T-palm formation. Down here to the south, it's late Miocene, 8 MA. And then the magnetostratigraphic section I shows up here is in the northern part of the fold belt, and here we get the depositional ages in the T-palm formation are 3 to 4 MA. So we do see this sort of long-term progradation of the delta, and it's likely being moved westward as the fold belt advances. Right. So it's the present day Brahmaputra River here follows actually the western limit of the deformation front as defined by buried anticlines beneath the modern Ganges Brahmaputra delta.
Great, thank you. So then we've got another question by Vitali.
who asks, can we extract a signal from the sediments about the tectonics, which you elaborated on, but specifically Vitaly asks about uplift of the Shillong Massif and the formation of the Dalki. I think that, I'm sorry if I mispronounced that, four deep and tilting potentially.
Yeah, that's a really great question. I'll just use this map here. So for those that aren't familiar, this is the Shillong Massif here. This is a block of Proterozoic Indian craton that's being uplifted along a north dipping crustal fault, right where my cursor is, called the Dalki Fault. And it's overthrusting the northern part of the Indo-Burman fold thrust belt. And the load of this overthrusting massif is creating a flexural foreland basin here called the Sylhet Basin. And so there's a nice suite of papers by Yanni Najman and more recently Paula Berge, and also Rashid Abdullah, that look at 2D reflection seismic data across the Sylhet Basin. And you can see quite clearly in that data that at the top of the TPOM group and certainly the Dupatilla group are growth strata related to the propagation of the fold belt. So that means that they're being deposited during flexural subsidence of the Sylhet Basin here. I don't see that signal in the data that we're looking at because it's one, older, and two, a little bit far from the Shillong Massif. However, I did test for Shillong sources in our Indo-Burman data by looking at this compilation of zircon, uranium, lead ages. These are actually from plutonic rocks that intrude the Proterozoic crust of Shillong. This data is from an Onion paper, 2010, I think. And the issue with Shillong is that it's Proterozoic Indian crust. So its DZ uranium lead signal is going to look just like the Lesser Himalayan series. Now, when I did the inversions, including the Shillong bedrock terrain, I did not see any significant contribution to the Myocene and Pliocene part of the section, and certainly not the Oligocene part of the section from Shillong. And I think that really just by comparison, the exhumation of Shillong is quite a small catchment compared to the extent of the entire, modern and late Miocene to Pliocene Brahmaputra watershed. So it's probably not contributing a huge amount of sediment to the Miocene and even Pliocene delta, although much of the sediment of the Dupatilla group that's filling the Sylhet Basin now is derived directly from Shillong Massif. So hopefully that answers your question.
Yeah, thank you. I got you.
Sure.
Great, thank you. Do we have any other questions from the audience?
For our speaker today. I have a minor question myself.
Yeah, sure.
For other people to kind of cue their thoughts. It's a very simple question. So with a lot of the marine sediments that you were looking at in the central IBR, again, beautiful section, really jealous. Did you ever see evidence for, let's say, mass wasting coming off from, let's say, like a accreting prism or anything like that coming into your?
Yeah, that's a great question, and I don't think so. Everything is pretty well vetted. I don't recall seeing any mass wasting deposits in the Surma group.
Yeah, I was just curious because I had heard of such things in other parts of the IBR, but I wasn't sure if there had been records of that in some of your sections. So
yeah, I know there's in seismic, Claude Rengin and Thomas Morin have published papers offshore of Bangladesh and the Arakan coast of Myanmar here, and there's certainly lots of evidence for mass wasting deposits there, the collapse of the shelf edge. But looking at the road cuts that we have here in Mizoram, I can't think of any particular outcrop that is clearly mass wasting deposit. They may be there, I just haven't seen them or didn't recognize them.
Yeah. Okay. Cool. Yeah.
it's an interesting food for thought in a couple of ways. Yeah. Cool.
Yeah.
All right, any other questions burning in your brains? No? Well, in that case, you're off the hook, Paul,
right.
now, after giving a wonderful presentation today. I love a good provenance story, and especially consideration of anything with tectonics versus climate altogether. And yeah, incredibly rich data set. And I very much enjoyed the way that you gave credit to a lot of people who've done a lot of work here, not only for the work that you've done. So I think it was a really nice presentation. So let's put our hands together for our speaker today. And before all of you run away, I would like to also remind everybody that next week, we also have another monsoon seminar series on the Schedule A. So just refer to the website for that, or from the various emails sent by us hosts. And that will be Coralie Zorzi next week. So that's pretty much it for today.
Thank you so much.
All right. Thanks very much. Appreciate it.
Right. Thanks for joining. And I hope everyone has a really good rest of either your evening or your afternoon or your morning, wherever you're joining us. So